Okay, so without any further delay, we start the class. Okay, I should keep the room unlocked. Okay, so I've kept the room unlocked and okay, so let's begin. As I've discussed about this lab in the previous class as well. So this is a simulation program with integrated circuit interfaces, SPICE. Sorry, I didn't change this actually. I will update that also. These are the contents of the lab that we'll be covering. Maybe some of the some part of this. Okay, and we'll continue to see different things, even addition on these things. Okay, in the previous class, I have given you the list of the simulations that we intend to perform in our lab. So we'll be performing those experiments or simulations here in the lab. So what is a SPICE? Okay, is a general purpose analog circuit simulator that is used to verify circuit designs and to predict the circuit behavior. Okay, so what we can do, it is used to verify circuit designs and predict the circuit behavior. We can perform these two tasks. Okay, so if we have designed a circuit, we can verify whether this is functioning properly or not, because when we design, we know what would be the expected output. So we can verify the design and predict the circuit behavior. Okay, once we know what we have created the circuit, after creation of that circuit, we can predict by simulating the circuit behavior. In this, we can predict how the circuit is behaving. Initially, it was developed by the University of California at Berkeley. PSPICE is a PC version of SPICE, and HSPICE is a version. There is another version of PSPICE, that is SPICE, that is the HSPICE. There are other LT spices also there. Star Spice is also there. So there are a lot of different versions of PSPICE are there. Spice are there. Okay, here what we are using is PSPICE. Okay, PSPICE is a PC version of Spice. PSPICE has analog and digital libraries. There are certain libraries which we can use directly, okay, of a standard components such as NAND, NOR, flip-flops, digital gates, op-amps. There are a lot of ICs in the library. We can use diodes. There are different number diodes are there. Transistor libraries are there in the SPICE. Okay, so many libraries are there in the SPICE, which make it a useful tool for a wide range of analog and digital applications. Okay, it may not be visible here. Here are some links. Okay, these are some motivation why we do or why do we prefer this. Okay. So reference books. This is one of these two books are most used books. Okay, and this PSPICE second book here. PSPICE using ORCAD for circuit and electronics. So I think if you have chance, you can purchase this book. Okay, because if you can get nearby you, you can purchase this book. This would help you to understand the spice completely. Okay, so this is one of the best book on spice. So you can purchase this book. Okay, one second. Okay, yes. So what is the file structure? What is the file structure in Spice? Actually, there are each file has different extensions. Okay, so we can use different extensions to write different files, like input files for PSPICE that has the file type CIR. Means if you will write a code that file, okay, so we will write the program, okay, circuit description, then we will save that file, whatever name you want to give, name.cir always, okay. So the name.cir will be the extension for the input file, okay. This type of file can be simulated by the PSPICE. So we have to save each and every file by the name or by the extension of .cir. Okay. So whatever name you want to give, we will give the name .cir. Like for example, if I write here like test.cir. Okay. So there's the file name is test.cir. So this is about the input file that it takes. When a circuit is simulated, .out file is automatically generated. Once the simulation is done, the .out file is generated, where you can see all the nodes, input voltages and node voltages and currents. Okay, and other commands we will give to calculate different things. We can check those things also in the output file. Okay. .dat. Okay, this is another type of file that we see in the SPICE. Is by default a binary file to see the data. If you want to see any waveform, we have to we will see the file, and that file extension will be .dat file. Okay, and one more file types are there, that is the .lib. This is for the library files. Okay. So in the library files, normally the details of the complex parts are saved. So we can save the details of complex parts in the library. Okay. So what are the info? So here, what is important for you? Okay, all are important for you, in fact. But what you will encounter again and again is the saving of the file, input file, because you will be creating an input file and you have to save it as .cir. So whatever name you want to give the name and keep it as .cir. Okay. Okay, so next thing that is very important to SPICE is PSPICE is not case sensitive. Okay, whether we use uppercase or lowercase to writing things in the SPICE doesn't make change. Okay, even if we use capital or small, if resistance is represented by R, so if we write small r to represent resistance or the capital R, it doesn't change. Okay, if you write small r and capital R, it will consider two things as the same things. Okay? All element names must be unique. Okay, that is why you cannot give two resistance, say two components same name. Means two resistances cannot have the same name RR. You have to give the different names like R1, R2, R3, like this. You have to make the difference. There must be a node designated as 0. Okay, this is the reference node against which all the voltages are calculated. So there must be a node of 0. Okay, so every component is connected. Every component is connected between two nodes. Okay. And in the SPICE, one node we have to give as the reference 0, and others voltages will be measured with respect to that ground node. Okay, which we call as the ground as well. If any change is made in the circuit, make sure you create netlist again before simulating. Netlist means where we give the different nodes. So you have to give those things again. Okay, you have to verify it that you have change it properly. Okay. Startup and the basic syntax start programs. Okay, so how we can start it? I'll show you that after some time. Okay, how we will start this SPICE and how we will begin this. I'll show you this in a very short time. So let's see. There are 5 different commands you can use. Okay, starting how we will start the SPICE, where it is available. We can see this after some time. Okay, but how we'll see, these are the different 5 commands that we use in the spice. Okay, so the title, remember this, first line of code is always title. Okay, first line. Okay, so that is why you never write the first line, any code in the first line. First line is by default, take it as the title of the lab. Okay, title of the simulation. Okay, so whatever the experiment or simulation you are doing, you can give the name of that simulation on the first line. That is, you can call the voltage divider. Okay, rectifier. Okay, half wave rectifier, full wave rectifier, clipper, clamper, whatever is that, you can give the in the first line. One thing. Second thing is that dot end. Okay, always the code of your circuit will end with dot end. You have to write, after writing the complete code of the circuit, in the end you have to write dot end. Then there is third, comment. Okay, comment line denoted by star. If we write star and then we write anything, that is considered as the comment. Okay, that is considered as the comment. Elements, we can connect multiple elements like resistor, capacitor, transistor, diode, ICs. Even we can connect all those things in our circuits. Okay, and then there is control commands, means it decides what type of analysis you want to do. Okay, in a spice we can perform 3 types of analysis. The DC analysis, where the voltages, input output voltages are DC only. The transient analysis means the input output voltage depends on time. And the AC analysis, where the we want to study the variation of output with respect to the frequency. So there are 3 types of analysis, and all these 3 can be performed in the spice. Okay, so before we move ahead, let me show you these 5 different things in one spice program. Okay, so let me start this spice. So first I'll go into the search. So I can search it here. So if I write PSPICE, so you can see that this spice is PSPICE ADS. Their ADS analog digital. We can use this spice for analog and digital both. Oh, okay. Actually, I didn't check. I thought it is installed, so I didn't check it before starting this class. I checked it was there. There is some license problem. Give me 1 minute so that I can rectify this problem. Okay, so let me show you how to start the spice. Okay, so I searched spice here in the search box, and the spice is started now. You can see on the top left corner that file, view, simulation, tools, windows, etc. Many things are there. Okay, so many things are there. So how we can start a file? uh, Click on the file, go to new, then a text file. Okay, so if we click it here, a next new text file comes here. Okay, we can directly start from this point as well. This is also from here also we can, in the top left and left corner you can see. Okay, there if we click on this directly, the text file will open. You can see that text1, text2. I opened the second one. So the okay, so we can open multiple files as well. Okay, so the first line, this I will as soon as I started this, the first line should be a title. So let's say this is a this is a test, so I write a this is a test file. Okay, so this is a test file, so this is a title of the file. Okay, so this is the title of the file. So how we define, then in after the test line we write the command, we write the description of the elements, like just I'm giving one example, that like resistance 1. Because how resistance is connected to resistances, you can see resistances are connected between 2 nodes. Okay, so resistance is always connected between 2 nodes. So what we are going to use it, Yeah, so like resistance is connected like this. So this is the resistance connected. Okay, so this node may be 1, this node may be 2. Okay, if I connect the next resistance here, this is suppose ground. Okay, so this resistance R1, this is R1 connected between 1 and 2, and this R2 is connected between 2 and ground. Okay, this R2 is connected between 2 and ground, and R1 is connected between 1 and 2. And let's say voltage source is connected between, some voltage source is connected like this. Okay, so let me take it as the DC voltage source, not an AC one. Okay. So this source is the DC voltage source. Okay. So this is an example. I am showing you different things. Okay. So first thing that we have talked till now is that we can write elements. So since there are two resistances, I am using R1 and R2. If I write here R1 or capital R1 or small r1, both are the same thing. So it doesn't make a change. So let's say this R1 is connected between 1 and 2, and let's say the value of R1 is say 1 kilo. Okay, so K we use for the kilo. Okay, so since by default SPICE understands that you are writing a resistance, it takes R as the resistance. Okay, so automatically it considers that the unit for the resistance is ohm. Okay, so this is the standard representation of a resistance in the SPICE. As soon as you write R, it understands that you are going to describe a resistance. Then we have connected R2. Okay, I write by small r2. Okay, so it doesn't make difference. If I write small r2, capital R2, doesn't make difference. Okay, also there is no relation between the name you give in the circuit and name you give here. Okay, it is for your understanding. Okay, जो आपने R2 यहाँ लाया तो R2 यहाँ नाम देंगे, it will be clear to you at all time. R2 is connected between 2 and 0, and let's say the value of R2 is also 1. Okay, so both are the same voltage. I have also connected a voltage source. Let's say the voltage source is Vin. Okay, this is a DC voltage source. Okay, so I give the name of the voltage source as the Vin is the voltage source, and Vin is connected between where? You can see this is ground. This is ground. Okay, so you can connect the two as well because both are grounded. Okay, so this ground is 0. So voltage source Vin is connected between 1 and ground. So this is 1 and 0. If I make this 0 and 1, so it means this will reverse the polarity of the voltage source. It means the negative will go upside and the positive will come downside. Okay, so 1 and 0 I am giving means the positive voltage is at 1 and the negative terminal is at 0. Okay, let's say this is 5 volt. Okay, I am writing here DC 5 volt. If I don't write DC also, it will understand that this is DC. By default, it understands DC. If you want to write AC, then you have to specifically specify that it is AC. Okay. So if I don't write the 5 volt also, it will understand that it is a voltage because the first letter for its description that we use is V. Okay, V is by default a voltage source in the SPICE. Okay, so if I write here V or not is the same thing. Okay, so this is important thing. Okay. So the first line is always resistance. Okay, one more thing is there. I will write after some time. Then let's say I have entered 2-3 times. I have given the enter, and then let's say the program ends. So how we end the program? We write dot end. This is the end of the program. Okay, so these are the description of the previous slide. Okay, the first line is always a test line, command, sorry, the title. Okay, then we write the elements, and the last line is always a dot end, which tells us that the program ends here. Okay, and these are the element descriptions. Okay, now what is important, another thing important is that we have to give the name. Okay, let's save this file. Save as. We go on to the file, click on save as. So there are so many files. Let I give this name as that circuit file, and let me the name for this file is test. Was already many tests are there. Okay, so lab1, and then what extension we have to give .cir. Always give this extension lab, whatever the name you want to give, .cir must be there. This is how we represent our file. Okay, this is how. So this CIR is important for you. Okay, don't forget the CIR. Okay, so this .cir tells us that we are describing a circuit file. Says .cir is an extension of circuit file, is a compression of circuit file. Okay, so once we have written this, we can save this file. Save. Okay, so the file is saved. Okay, so the file is saved now. Okay, if you want to open, okay, so we can file, open. So all so many files came, but you see that you want to open a circuit file. So file of type it is showing here is .dat file. Okay, but we want to see a circuit file, so we'll select here and select the circuit files. Here it is the circuit file, so we select it here, and we have what was the name, lab1. So lab1 came here. Okay, and you can see here also that where is the lab1. This is the lab1 here. Okay, so lab1 circuit file we have selected, and it is now open. Okay, so now the file is opened, and you can see the name of the file, the lab1 is visible here. Okay, the file name is visible here. Okay, so let's go back to our presentation. So this was a description of the previous slide. Okay, so there are 5 types of command: a title command, the end command. Then we have not given any comment. Okay, let's give one comment here also. Okay, this is a test comment. Okay, I go, oh, sorry. Any text you want to write, you can write it. This is a test comment. So it will not read this. So it will not read this line. Okay, so whatever we write after this star is not read by this. Yes, Laiva, do you have any doubts? You have raised your hand by mistake or deliberately. If you have any doubt, you can ask Laiba. Okay, I think it's okay. So this is how we write a comment. So we have talked about the title, we have written dot end, we have written comment, we have written element, we have described voltage, resistance, we have described there. We have not written any type of analysis yet. Okay, I will write those analysis. First we will see the analysis, then we will write about it. Okay. Yeah. Okay. So Sorry for disturbance. Okay, so what are the these are the two important commands: dot probe and dot print. Okay, dot probe is a graphical results analyzer. Okay. When we keep this dot probe in our program, then only it can show the graphical results. When PSPICE complete the simulation, probe plots the waveform results so you can visualize the circuit's behavior and determine the validity of your design. Remember this, don't forget this. Okay. So probe once the simulation is finished, whatever the function we are doing, our circuit is performing, this will be displayed by in the graphical plots. Okay, this is done by the probe. Okay, dot print, this command was designed to work with DC or AC. Okay, nowadays we don't need dot print. If we keep dot probe in dot probe alone is enough for describing the result analyzer. Also, this also gives the same thing. Okay, if you want to particularly display one voltage, we can keep dot print and that voltage name, and it will display that voltage only. But in dot probe, it gives the list of voltage whichever you want to plot. You can click that voltage, and that voltage will be displayed. Okay, so this like print is specific, and this probe will give all the voltages. Okay, you can select which you want to display. Okay, so we will see the display of this program also. So we keep it here dot probe here. Okay, so dot probe, again you write capital or small, doesn't make a change. Okay, we can use any of these. Next thing. Okay, so I keep it here because we want to see the graphical results. Okay. So next thing is the passive component description: resistance, capacitor, inductor. These are three passive components that we can define in the SPICE. Okay, so resistance, I have already told you that resistance name, okay, means R1, R2, whatever the name we want to give the resistance. So R1, R2, R3, like that. So R name, then node 1. Okay, so node 1, let's say the resistance is connected between 1 and 2. Node 1 is 1, node 2 is 2, and the value is 100. Okay, so by default it understands the unit is ohm. Okay, so this resistance is 100 ohm resistance connected between 1 and 2, and the name of the resistance is R1. Similarly, you write the capacitor. Capacitor, the C capacitor is represented by C. After C, we can keep C1, C2, C3, or C bypass. CB, YP, here it is written to specify the bypass resistance. Then the node 1, let's say the resistance is connected between the node 13 and the node 2 is 0, 13 and 0. Okay, and 1 UF. Okay, here you remember that we have written the U. Okay, there is no standard sign of micro in the so this is used directly. Okay, so one U is used to specify the micro. If we write F, it will understand. If you don't write F, we also understand that it is a capacitance, because by default the capacitor unit is farad. Okay, so the SPICE understands this F by default. Again, the third component is the inductor. Again, the same format: inductor name, L1, L2, L3, node 1, node 2, and the value. Okay. Units in SPICE, this is very important how we specify different units. Okay. So if we want to write tera, we write T. If you want to write giga, we write G. But if you want to write mega in SPICE, that is the 10 power 6, it is represented by MEG. Remember this. Mega is not represented by capital because we represent milli in small m. Okay, since we represent milli in small m, this milli is represented in a small m. So if you write the capital M, and SPICE does not differentiate between the small and the capital M. That's why we do not write mega in the capital M. How otherwise we write although we write mega by MEG. Okay. Then kilo is represented by K, micro is represented by U, nano by N, pico by P, femto by F. Okay, so these are the units that we use in the SPICE. I hope you understand this. So the difference is at mega. Others are the same. You can use it by yourself. Okay, the difference is at mega. So MEG is for mega. So again, there are actually specific design formats for the dependent and the independent sources. Okay, so we'll tell you about the dependent sources at some other point of time. Okay, dependent sources can be voltage source or can be the current source. Okay, and both can be for the voltage and the current, dependent and independent sources. So how we write the independent sources? Independent voltage source is written as volt V. So first letter must be V. Then we give the name, whatever name we want to give. Okay. Then there is the name, and then node 1, then node 2, DCAC, and then the value. Okay. So like this, it is VCC. Name of the voltage source is VCC. Node 1 is 10. Node 2 is ground. This is our DC type, and the voltage is 6. By default, if no V is written here, it means it is the voltage. Okay. And similarly, we can write the independent current source I underscore N. So, okay, so I underscore N is the name of the current source. It is connected between 10, 0, AC, and 3 milli is the value of the current. Okay. So in this program, here in the same test, we have connected the voltage source between 1 and 0 at the this is DC and the voltage is 5 volt. Okay, we have already connected one. Okay. So whether it is DC or AC, we write in the same format. Only thing changes is the DC name here and the AC name here. Okay, only this thing changes here. Abhiya, why you are unable? Still you are unable to join? I think you might have joined by now because it is already too late. Okay, so DC voltage name mode 1, mode 2, then the DC value and the AC magnitude. These two things are the same. We can give the for AC the magnitude and the phase as well. Okay. Next thing is a transient. Okay. We can apply a time dependent voltage source also. So before we come to the transient, we will see. We'll like to see one example of DC voltage source. Okay. Let me. Okay. So we have written this program, and you can see that this voltage output voltage is DC voltage. Okay. Output voltage is DC voltage. So what we are going to do is we are going to learn about the DC analysis. Okay, since the voltage input voltage is DC only, so how we can perform the DC analysis of this circuit. Okay, we will come to the transient after this example. Okay, so DC analysis. So DC analysis, DC transfer curve, source and sweep. Okay, so how we perform the DC analysis. Okay, so for this we give this dot DC command. Okay, this dot DC tells us that the DC analysis is being performed. Okay, so if we write dot AC, it will tell us that we are going to perform the AC analysis. If we write dot tran, that tells us that we are going to use the transient analysis. Okay. Then after .dc we give the name of the source which we want to vary. Okay, see the circuit that I drawn here previously, I think let me quickly draw it here. Okay, this was the circuit. Okay, so you can see if we give a DC voltage, Suppose if I give 5 volt here and this is 1k, this is 1k. Okay, so if I give a fixed voltage here, so you know how much voltage will come here. This by voltage divider rule, you will get how much voltage here. 2.5 volt you will get here. Okay, you will get 2.5 volt here. 2.5 volt. Okay, by voltage divider. You know voltage divider, what is that? R2 over R1 plus R2 times voltage source. Okay, so by voltage divider we will get 2.5. So if we give 1 voltage input, we will get 1 voltage out. But we don't want to give 1 voltage level. We want to see the variation. Okay, so we will give some sweep or variation to this 5 volt voltage, and then we can check the corresponding variation in the output voltage here. Okay. So yeah, so we have to give some sweep in the circuit. So this is how we give the sweep. This is a starting point. Okay, we start from which the voltage start. Okay, so this is like the starting point of the input voltage. This is the next is the stop point of the input voltage. Then the increment. Okay, how much increment you want to give continuously. Okay, I'll tell you this thing in our program as well. Then this is like for one source. If there are multiple sources, voltage sources, we can give the same thing for the source 2. Again for source 3, like this we can continue like this. Okay, so let me complete our program. So what we have done here, we have written the voltage source. Only thing is left is the DC analysis. I'm deliberately using .dc, capital sign. I'm using .dc. We can write small as well, no problem. I told you this many times. Okay, .dc. So this tells us what this .dc tells us, that DC analysis is going to be performed. So what is the voltage source? Voltage source is our V in. Okay, so V in. I have written here capital and there is small, no problem. Okay, and then the starting point. So let's say the starting voltage was 0, maximum voltage will go 5 volt, and let's say the step is 0. Let's say we can make it 1 volt as well. Okay. So this three things written shows that the starting voltage will be 0, then the voltage, then the output will be calculated. Then input voltage will change to 1. Okay. So the how the steps work. Okay. So 0, then 1, then 2, then 3, then 4, and then 5. So at input is 0, output will be calculated. Input is 1, output will be calculated. Input 2, output will be calculated. Input 3, output will be calculated. 4, output, like this. This would continue. If we can make this step size smaller as well, like this is 1, then we can calculate step size of 0.1, then 0.2. So more number of calculation will be there. Okay, so if we give the change the step size here to be 0.1, then it will change in the steps of 0.1, 0, 0.1, 0.2. So like this. So 0 पर output calculate होगा, 0.1 पर output calculate होगा, 0.2 पर output calculate होगा, 0.3 पर output calculate होगा, and this will continue. Okay. So if meeting stops, don't worry, I will restart the meeting. Okay, so let me remove these drawings. So I think the file is completed. Everything is completed in the file. Okay, whatever we want to write about the file, we have written. The test command, so first line is the title. Okay, after this we can write the complete circuit description. Then we write this is the comment line. This line dot dc. This is called the control commands. Okay, so these are called the control commands. Then dot probe is kept to visualize the result, and then dot end. Okay, I have already saved the file. If I have not saved, I would not have saved this file. What I have to do, I have to save this file .cir. I will save the file. Then after saving the file, we will again open the file. Only after that we can simulate it. Okay, since the file is already saved, so we can simulate it directly. Once I click the save button here again. Now you can see here a blue arrow is coming here. Okay, if it is not saved and it is not ready, so it will, this blue will not come. Okay, once we save the file and open the file, this blue will comes and this, it tells us that we can run. See, I have kept the arrow, I didn't press this, but you can see the run is coming here. So we can simulate by here, or another, we can click on the simulation. You can see here simulation tab is coming here. If we click on simulation, we can click by run. Okay, here inside the lab is run. So by anyone we can select it, we can run it. So let me run this. So as soon as I've run this, you can see automatically this black window came. Okay, so automatically this black window came. So, and you understand, okay, where we are taking the output we are taking at the resistance 2. Okay, I will be having the circuit. It is okay right now. Okay. Okay, so we are performing DC analysis. Okay, so you have you know the circuit. What? Okay, so we are calculating the output at resistance 2, which is connected at node 2 and the ground. So we want to plot trace. Okay, so where is that one? There. Here by clicking on this tabs, we can move to the text file and the simulation file, the result file, wave analyzer. Okay, so we can change our tab. Okay, so now we are here. I want to trace. So what we go to the trace and add trace. Okay, add trace. As soon as you give this add trace, so you can see all voltages, currents related to the voltage related to our circuit is visible here. So okay, so the current flowing into the R1, current flowing into the R2, V1 voltage, that is the input voltage. Okay, V2 voltage, that is the output we are considering. So we are interested in V2. Okay, we want to see the V2 voltage. Okay. Now you can see that this voltage is varying linearly. But you remember what is on the x-axis, and we plot the curve always with respect to x-axis. Okay. X-axis is an independent variable and y-axis is the dependent variable. And you can see what is on the x-axis. In x-axis we have our input voltage. Okay. What we have in x-axis is our input voltage. Okay. So you can see in the x-axis that input voltage is, this is input voltage. Okay, so input voltage is changing here and output voltage is changing on this y-axis, and corresponding input, what is the output is calculated here. Okay, or on the online here. Okay, so these lines that we are seeing here, dotted lines, horizontal and vertical, these are called the grid lines. We can remove these grid lines. We can make a lot of changes on this window. Okay, we can increase the fonts. A lot of things are there that we can do. Okay. So this